in solid sphere we have in hollow sphere also we have two options. One is inside the hollow sphere, other is outside the hollow sphere. And we saw in the two sessions earlier that inside the potential is same as the surface, which is kq by capital R, and outside it is kq by R. We can derive it by using E is equal to minus dV by dr. Very easy thing, right?
Yes, sir.
Now, for solid sphere, and it's a uniform solid sphere, that means our rho is a constant. Charge per unit volume is a constant. So here we have two cases. One is inside and the other is outside, right?
Yes, sir.
So first let us look at inside. What is the electric potential inside the solid sphere? Basically, let's say we have a solid sphere. Whose radius is capital R. Okay.
Yes, sir.
We want to find the potential at a distance of small r from the center.
Yes, sir.
So if you remember, we did electric field also, inside, outside, solid sphere. To find the potential inside, again we will have something called inside outside.
Yeah.
Right? So basically what I'll do is, at a radius of r, I am going to draw a sphere basically.
Yes, sir.
Okay. So I want to find the electric potential at this point, which is at a distance of small r from the center. So let's say center is O and this point is some P. So all we are saying is that the distance OP is small r. And we are trying to find the electric potential at this point P. Okay.
Yes, sir.
Next, I drew a sphere, imaginary sphere using these dotted lines with concentric spheres with O as the center passing through P.
Yes.
This imaginary sphere will divide my bigger sphere into two different sections.
Yes, sir.
One section is this inside section and the other section is the outside section. The outside section is basically the one that I am basically highlighting. Okay.
Yes, sir.
The entire thing is the outside section. Okay. And inside my sphere is what I am calling the inside section. Fine?
Yes, sir. Yes, sir.
Now, to find the electric potential at point P, the element that I am going to take for a solid sphere is a hollow sphere. Okay? Fine?
Yes, sir.
So, this inside is basically finding the electric potential at point P. Correct?
Yes, sir.
And that point P is inside my sphere. For this inside case, I have two subcases, which again we call it as inside and outside, right?
Yes, sir.
So again I am writing subcase A, which is due to inside of this sphere, imaginary sphere. So we'll write inside of imaginary sphere. Are you getting my point?
Yes, sir.
Now, to find the potential due to the inside material of this imaginary sphere, due to that material at point P, I will take an element of radius x and width dx. Okay, I am taking an element of radius x and width dx. Is this clear?
Yes, sir.
This width it will have dx and the charge it will have is dq. Right?
Yes, sir.
dq is equal to rho into, actually that particular width which has dx will have a volume, right?
Yes, sir.
So my dq will be rho times dv.
Yes,
Okay.
sir.
And what is my dv?
4 by 3 pi r.
No.
Oh, for the smaller one, no? Then it will be the area into the
What is the
dv,
area?
4 pi r square.
So here we will have it as 4 pi x square and into
Yeah.
the width which is dx. Okay.
Yes, sir.
So we know dq now with this in terms of small x.
Yes, sir.
What is the potential due to this small element dv?
Yes, sir.
Uh,
AD, ADQ by.
yeah, dv inside. Why I'm writing inside is due to the inside material. Okay, is equal to k dq by
Vx.
So basically, what do we have? We have a hollow sphere of radius x. So I'm not showing
So
width
from
d.
there it will be r, sir.
So what is the potential? K dq by
R.
r. Basically, we need the distance from the center.
Yes, sir.
K is a constant, r is a constant.
Yes, sir.
So we'll have integral of dq, right? So if I have to find potential due to inside
AQ by
material,
R.
yeah, due to inside material is k by r integral of dq, and the limits of dq will be 0 to q inside, correct?
Yes, sir.
Because it's a uniform distribution, I don't have to go in that route. I can directly say integral dq is q.
Yes, sir.
If it was not a uniform distribution, if it's a non-uniform distribution, then rho will be a variable. Then I'll have to substitute that dq fellow everything over here. Are you getting my point?
Yes, sir. I
I'll
mean,
repeat.
here it is constant, that's why we
I'll
wrote
repeat.
some.
I'll repeat again. The potential dV due to the inside material, due to that element that we have taken at point P is k dq by r.
Yes, sir.
Here, for all elements, as x is varying, for all elements, r is the same.
Hmm.
So my k by r is a constant.
Yes, sir.
So I can write v in as basically integral dv, and I can take k by r outside and just write integral dq.
Yes, sir.
Here, I can directly write integral dq and also integrate directly because rho is a constant.
Yes, sir.
If rho would not be a constant, that means if it is a non-uniform distribution, rho would be a variable, then I would have not integrated dq directly
Yes, sir.
because q is also varying, the rho is varying. So I'll substitute all of that over here, and in that case, do my integration.
Yes, sir.
Okay.
Yes, sir.
But here I can directly do integral dq as q and substitute upper limit minus lower limit.
Yes, sir.
Is this clear?
Yes, sir.
Now, can I write this fellow as k q inside divided by r?
Yes, sir.
This is V due to the inside material at a point R, at a point P.
Yes, sir.
Clear? If the total charge of the sphere is capital Q, the entire charge distributed in the solid sphere is capital Q. Now I got something new, Q inside.
Yes, sir.
How do I get that Q inside fellow? What is Q inside in my diagram? Q inside in my diagram is basically this highlighted area. Are you getting my point?
Yes, sir.
And of course, I didn't completely fill it, right? We can fill it. That's not an issue. This entire black highlighted region is containing my charge inside.
Yes, sir.
Just for a small recap of just this story, we took a small element x having a width dx, now it is not visible.
Yes, sir.
Having a charge small dq, but we can write it as k dq by r. K and r are constants and it's a uniform distribution, so I can directly do integral dq. Therefore, I can directly write it as k charge inside divided by r.
Yes, sir.
Is this clear?
Yes, sir.
So, if my small r is capital R, that becomes this point P will come on periphery of the solid sphere.
So we can write A
Total Q
inside by R.
divided by capital R.
Capital R, yes, sir.
And Q also is total Q in that case.
Hmm.
Okay, now the
So
highlight,
Q is constant, right? No.
which is constant,
Q. Everywhere it's Q only.
everywhere its Q has no sense. I have 1 kilo rice. I'll say 1 kilo is constant because everywhere there is 1 kilo. No, I have 1 kilo rice. Everywhere I have rice. Everywhere I have charge. Total is capital Q.
Okay. Yes, sir.
So total charge inside the total sphere is capital Q. But we have divided in the potential at point P, which is inside, point is inside the solid sphere. In that also we divided into due to inside of the imaginary sphere region, which is my black highlighted region here. And due to that, I got it as K charge, which is inside divided by small r. And now I have to find what that charge inside is in terms of capital Q for my own better understanding.
Yes, sir.
My charge inside I can find using my rho actually, because everywhere the charge distribution is uniform. Actually, rho is what? Capital Q divided by total volume.
Yes, sir.
Total volume is 4 by 3 pi r cube.
By 3 pi R.
Capital R in this case. Now I have something charge inside story, right? This
Yes.
is the black highlighted charge that I have inside the imaginary sphere, right?
Yes, sir.
Divided by what volume will come over here? 4 by 3 pi?
Therefore, pi small r cube.
Good. So eventually my charge inside is equal to r cube by capital R cube into capital.
And dq divided by.
Even dq divided by dv. So from here, we got charge inside is equal to small r cube by capital R cube into capital Q.
Yes, sir.
If you remember, for electric field, we already did this. You should, if you remember, or you can go through the derivation after lecture. We've done
Yes.
that. What is the charge? Ratio of r cube by r cube into capital Q. We did the exact same thing and got that information. Just I wanted to remind you. So basically, eventually my answer will be what? KQ. What will come over here? Small r cube by capital R cube. Correct? Divided by small r.
1 second. I understood, sir.
Okay. 4 by 3
Yes.
pi, 4 by 3 pi will cancel. I have
Yes,
capital
sir.
Q into. If you remember, in electric field, we had r square here.
Yes, sir.
That cancelled with r cube and it was r.
Yes, sir.
Then I showed you in graph electric field versus r is a straight line, y is equal to mx.
Yes, sir.
Okay, fine. But here we have denominator r. So only one r will cancel. So the potential due to my inside material at point P is equal to K capital Q by R cube into R square. Clear?
Yes, sir.
Fine.
Yes, sir.
Just a
And if we want to find the potential, like in the area you put blue lines, right? So we can take like the total potential, like subtracted with this one.
I didn't understand.
Then highlighted the blue with blue color marker, right?
That is the outside material.
Yes, sir. So
Yeah.
not that, in between of that. If we want to find in between of the outside and inside region.
We have to find at point P.
Oh, we have to find only at a specific point.
But anyways, everywhere on that sphere, potential will be same due to
Yes, sir.
symmetry. Okay, let us do outside part and then we'll see.
Yes, sir.
So when we are doing outside, what do we mean by outside? Due to this blue, so due to this particular region, right? Due to that charge.
Yes, sir.
So we are in subcase B, which is due to outside of imaginary sphere. Okay. Due to outside of imaginary sphere. Okay.
Yes, sir.
Again, I will take a element, concentric element of let's say of radius t. So this radius is t.
Yes, sir.
Okay. And that width we will take it as dt. Are you getting my point?
Yes, sir.
Now this figure has become complete kachra. So I'm highlighting this element over here with black. This. Okay. So I'll just draw over here. So I have my complete radius capital R. Okay.
Yes, sir.
In that I have an element at radius T having a width dt. So this fellow will have a radius T having a width dt.
Yes, sir.
The limit of T is from small r to capital R.
Yes, sir.
Whereas the limit of x over here was from 0 to small r.
Yes, sir.
So in one figure, it became complete kachra. Obviously, it is going to become, right, as we keep on doing things in the same figure.
Yeah, but we can take it from the previous case itself, like at a distance of x, then we can integrate from 0 to r.
Yeah, but I felt you will be confused. If I take same variable x over here,
Okay.
I felt you will be confused. So we can actually take an element x with a thickness of dx. And we can say when I define, actually if you see mathematically, inside automatically is mathematically defined as 0 to r, where x tends to 0 to r.
Yes, sir.
And mathematically outside is defined as r to t, r to capital R, sorry, small r to capital R.
Yes, sir.
But I felt you will get confused because anyways our every calculus element is an imaginary story, right?
Yes, sir.
So it's a variable imaginary story. So we can choose one variable and define the limits. And by defining the limits, things will automatically set up. Okay, done.
Yes, sir.
Now, my point P itself is inside this element. Obviously.
Where did you mark it, sir?
Here it is over here. Point P.
Yes, sir.
If you remember, I had a blue imaginary sphere that I am writing.
Yes.
Was at a radius of small r. And
Yes.
inside that sphere is what we did over here. Outside that imaginary sphere is what we are doing over here.
Yes, sir.
What I'm trying to say is, if you see this case, my point P lied outside my element. Whereas for this case, my point P lies inside of my element.
Yes, sir.
Too much of inside, outside, inside, outside. One of the reasons why kids get confused.
I understand.
Right? For my element, my point P is inside. So inside a hollow sphere, we already did, right? It is kq by whatever is the radius of that sphere.
Yes, sir.
In this case, I will get my dv due to outside at point P is equal to k dq divided by
It will be T.
t, the radius of my hollow sphere, which is t in this case. Correct?
Yes, sir. Sir, but the arrows which we took, shouldn't it be in the opposite direction?
What?
The arrows which we took, shouldn't they be in the opposite direction?
Arrows. Which arrow?
Like the direction of T, you took it from the center to.
It's radius, right?
Yes, sir.
So radius will start from center to.
I mean, but the potential we are calculating from the outside, right?
The potential that we are calculating
From outside to inside.
is due to outside region at a point inside.
Yes, sir.
Okay. Which arrow? You said some arrow.
Potential is a scalar, so you're not representing anything.
Yeah, that's what right? Fine.
Yes, sir.
See, our dq will be what? Rho into dv.
Yes, sir.
Here my dv, in place of x, I'll have 4 pi t square dt, correct?
Yes, sir.
And because there is small t over here, I'll have to substitute this entire story here. That's the importance.
Yes, sir.
Earlier I had smaller, it was a constant, so no problem. Here I have t, so I'll have to substitute this one. Okay,
Yes, sir.
is equal to k we'll have to substitute the entire dk thing. Is equal to k dq, we'll have to substitute rho 4 pi t square dt, correct?
I am substituting here, sir, over there.
Why are we substituting this dq over here?
Yes, sir.
Because in denominator we have a variable t.
Okay. Yes,
Here
sir.
we had a constant smaller and our variable
Yes.
was x. Okay,
Yes, sir.
so v due to outside material at point P is equal to integral of this constant k rho 4 pi, right? T square by t is nothing but t dt. Okay, okay.
Our cut.
Am I visible, audible?
Yes, sir.
Okay.
Yes, sir.
Limits of t is smaller to capital R.
Yes, sir.
Yeah. So my v due to outside material at point P is equal to, will write this story 4 pi k rho integral t dt is t square by 2.
Yes, sir.
From small r to capital R.
Yes, sir.
Yeah, I'll also have to substitute this rho fellow as capital Q by 4 by 3 pi r cube.
Yes, sir.
So v due to outside material at point P is equal to 4 pi k into rho is q by 4 by 3 pi capital R cube into upper limit minus lower limit. So I can write it as capital R square minus small r square divided by 2. Correct?
But for the limits, why can't we take it from 0 to R?
Because my t variable is varying from small r to capital R.
Yes, sir.
Because my highlighted
Minus smaller, it's like minus smaller to capital R.
minus smaller? What do you mean minus smaller? How can a radius be minus?
We are going backward.
Nobody is going backward. T
There the
is
element will go
T
inside.
is from the center. T is a radius.
Yes, sir.
There is no backward in radius. Radius always starts from center to wherever. Here there is a blue imaginary sphere
Yes, sir.
which has a radius of smaller.
Yes, sir.
Anything outside of that imaginary sphere is what we call as outside.
Yes, sir.
And the radius for outside material starts from small r and ends at capital R. Starts from small r and ends at capital R. The element that we were saying is, first of all, we took two different variables. For the material which is inside of small r, I took the variable as small x. Okay. And that small x is also a radius. All radii is usually beginning is from 0.
Yes, sir.
So the limits for my x is from 0 to small r.
Yes, sir.
For anything outside my imaginary sphere, I am taking the element as small t, which is also a radius. But the radius is starting from my imaginary sphere to the periphery, right?
Yes, sir.
My small t is starting from small r to capital R.
Sir, now what I'm saying is that R is moving backward. That's why it should be minus R to
Which r is
capital R.
moving? Which r is moving?
Sir, generally small r is defined from 0 to, like
From
going
center
ahead.
to point P.
Yes, sir, but the limits we are trying to go back and then go to the capital R.
For the limits, we are trying to go back.
Go to the 0 and then move till the capital R.
The idea of choosing a variable is that the variable tells me how I am covering my entire element, be it length element, areal element, or a volume element. My variable is telling me how I am covering the entire of my element, entire of
Yes,
my
sir. But
area
then
of
if you're going smaller distance backward and then going capital R
my.
distance forward.
Who is going smaller backward? Backward from where?
Element.
Backward from where?
From the radius.
From the radius smaller.
Wait, there's a gap between smaller and T, so we can't go like that.
There is a gap between smaller and T. Smaller
Yes, sir.
is the distance between center of the sphere and the point P, where we have to find the potential. This inside, first we wrote inside, is basically a point P which is inside the sphere. And we need to find the potential due to the inside point, potential at the point inside of sphere. Distance between center of the sphere and the point P is smaller. Clear?
I'm still not getting how did you take those limits?
I know. That's why I am asking. First, is the first part clear, which is due to the inside material? Yeah?
It's fine, sir. Just do that.
Now, I have a sphere of radius capital R. I have a point P of radius small r, right? I have an
Yes, sir.
imaginary sphere of radius small r. I have an imaginary sphere of radius small r. In my case B,
Yes, sir.
I am discussing of the region which is outside my small r. In my case B, I am discussing of the material which is outside of my imaginary sphere. Okay.
Yes, sir.
For the outside region which I have just highlighted, I have chosen a new variable t, which is also radius. Okay.
Which is also.
Radius.
Yes, sir.
From the center to a radius of t, I chose a small thickness dt hollow sphere. So what is t? T is the distance from the center of the sphere and it's a radius. At that radius t, I have a hollow sphere.
Yes, sir.
Having a thickness of dt.
Yes, sir.
The values of t will vary from small r to capital R. The values of t will vary from small r to capital R. Because that is only defining the outside part of imaginary space. Outside part of imaginary space. So my imaginary sphere started at R.
Sir, if you put total capital R, if you do total capital R minus small r, then you get the region's uh, radius, no, sir.
Volume of capital R minus volume of small r.
Yes, sir.
Volume, not radii. By subtracting radii, what will I get? Nothing. I'll have to subtract the total volume of radius capital R minus total volume of radius small r. That will define me the region which I am saying as outside of imaginary.
Yes, sir.
Volume, subtraction of volume will tell me how much do I have. But my variable, what is my variable? My variable is a radial line.
Yes, sir.
My radial line has for outside region, again I am drawing over here. What is my outside region in this geometry? The blue highlighted region, right?
Yes, sir.
My radius for this blue highlighted region starts from small r and ends at capital R. Starts at small r and ends at capital R.
I understood now, sir.
Starts at small r. What is my T? It's a radius, radial line. That's why I'm saying radial line is it's always starting from center. Has no meaning in going backward in radial line. Here.
I understood now, sir.
Anyways, so therefore I'm taking the radius the limits as small r to capital R, substitute it over here. I'll have capital R square minus small r square divided by 2. Okay.
Yes, sir.
I can cancel these 4 pi over here.
Yes, sir.
3 will come up. So I'll have 3 by 2 k capital Q r square minus r square.
Yes, sir.
Okay. Now, ultimately, the potential, see, I'm talking of this case.
Yes, sir.
At a point P, and this point is actually inside the hollow sphere, solid sphere, sorry, is equal to V in P plus V out P. What is this in and this out? This is inside region. This is outside region of the solid sphere.
Yes, sir.
Inside the imaginary sphere, outside the imaginary sphere. Okay. That means I have to add this. Huh?
Why are we adding? We have to.
There is a r cube over here. Again, you didn't remember me. Remind me. A cube by r cube is here.
Yes, sir.
Now, what are you asking?
Why are we adding, sir?
Adding what? These two? This is potential due to inner laddu. This is potential due to outside laddu.
Then
The
why
potential.
would it be inside, sir? It should be P total.
Huh?
Okay, you're considering now the overall from the overall sphere perspective.
I'm saying from the case. What case
I
are
understood, sir.
where point P is inside the sphere?
Yes, sir.
So the total potential inside the sphere at a radius small r is the summation of this and this.
Yes, sir.
So basically, I will have k capital Q by r cube. Okay, is same in both.
Yes, sir.
In brackets, I will have small r square plus this. I will have 3 by 2 into capital R square minus small r square.
Yes, sir.
What is this? 1 minus 3 by 2 is minus 1 by 2.
Yes, sir.
So here I have a capital Q by r cube.
We can bring 2 out.
2
Denominator.
also out, and inside I will have
3r square minus.
in my JEE subjective exam. One question came directly on this. Luckily, I remembered this, and I had to start from there basically, not do entire derivation. For that question, I needed to remember this and start from.
Yes, sir.
Okay, done.
Yes, sir.
Hi guys, I hope you enjoyed the session. If you think this video was useful, don't forget to like, share, and subscribe to my channel. Also, I'll be waiting for your comments in the comment section. See you in the next video.